email me and let me know. Okay, matrices day 1 is the title of today's notes. So what is a matrix? The definition of a matrix is it's a rectangular array of numbers. Okay, those numbers might be whole numbers, integers, could be negatives, could be fractions, rationals, anything in there that's a real number is good to go. Okay, the size of a matrix is known as the order of the matrix. So if you hear the term order, it means what size the matrix is. And I'll tell you the order is defined as being the number of rows that the matrix has by the number of columns. Okay, so since we have a number of rows by a number of columns, you can see here that we're going to get something that's a rectangular block of numbers here. So for example, if we have a 3 by 2, and hold on one sec, I'm going to yell at my dog who's eating something. Tango, get out of there. Okay, and back to math. Okay, 3 by 2, what would that look like? Well, it would have 3 rows, and then it would have 2 columns. So it'd be a row 1, row 2, row 3, column 1, column 2. And then you could put whatever numbers you want on the inside. You could have a 1, you could have a 2, you could have a negative 77, a 0. You can have pi. You can have, I don't know, negative 5. Okay, you could put literally whatever numbers you want on the inside, just showing you what the size and the order corresponds with. If, for example, I gave you a 4 by 1 matrix, this would actually be called a column matrix because it has a single column with 4 rows. So it's going to be a really skinny matrix with 4 entries into it. Maybe it's 1, 2, 3, and negative 10. Sorry if you really wanted that to be a 4. Okay, so we know what the size of a matrix looks like. Today, what we're going to do is look at a process called Gaussian elimination. And what Gaussian elimination does is it's a process that allows us to create a matrix using a system of equations. And then it's a methodical process that step by step allows us to solve the system of equations. And I'll tell you that in Gaussian elimination, first step is to create what's called an augmented matrix. I'll explain what that means in relationship to the systems that we're solving today. And then from there, once you've created an augmented matrix, your goal is to get the matrix in reduced row echelon form, which is a really fancy name, and I'll show you what that looks like. The abbreviation for that, and that we'll eventually see, is RREF, reduced row echelon form. By the way, all of these matrices will be, for our examples today, 2 by 3 matrices. And you'll see why once we start setting up the systems that we're about to solve. Basically, what we're going to have is we're going to have a system that has numbers in it that form a 2 by 3 matrix. I'll explain what this little wall that I'm dividing into the matrix will look like in a second, and why we have that there. What the goal is to make this look like the following. Reduced row echelon form has a 1 in the top left corner, a 0 underneath it. The second column would be 0, 1, and on the other side we'll have 2 numbers. There's even going to be a very specific way in which I want you to make the matrix look like this. You're going to start here and make that a 1. And then you're going to work your way around in a counterclockwise direction. So you're going to move down, make that a 0. Move across, make that a 1. Move up, make that a 0. How are we going to make all these 1s and 0s? Some things you can do to make this happen is you can switch rows. So for example, if there is a 1 in the bottom row and something that's not a 1 above it, you can actually take the entire second row and switch it with the first row. You're allowed to do that. Okay, another step is to make 1s. you can multiply a row by a constant. So if that was a 2, and I wanted to make that into a 1, I could take that whole top row and multiply everything by a half. And we'll connect this to what we've been doing, what we did yesterday with solving equations, and I think you'll see why that makes sense. Okay. And then the last thing is, what if I want to make some of those zeros? So to make zeros, you're going to multiply a row by a constant. And add it to another row. Okay. And if you're reading through all this and you're looking at all these directions and you're like, Mr. L, I have no idea what you're talking about, good. That's what you should feel at this point. None of this is going to make a ton of sense until we start doing some practice. I'll tell you, you may not even get it after the first example or the second example, but after example 3, 4, and 5, you're going to start to understand what this process is all about. And if by example 5 you don't get it, then I'm expecting an email waiting from you in my inbox. Okay. So let's see what we're going to be doing here. If I gave you a system of equations just like we saw yesterday, so we're going to solve this system here. So x plus 2y equals 5, and 2x plus y equals -2. Okay. The first step that we listed a second ago was to create an augmented matrix. That matrix was going to be a 2 by 3. So notice how I have 2 rows going across my matrix. And if I line up the x's, the y's, and then these answers on the right side, that would be 3 distinct columns. So the augmented matrix is going to look like this. All you're doing is taking the coefficients from the equations that we have in the top row and then in the bottom row and putting them into a 2 by 3 matrix. That line that I drew as a divider in the matrix was just separating those 2 answers on the right side from what I have on the left side. It's not necessarily something you have to include there. I think it's just nice to kind of keep things separated, because now my goal is to make the left side look like that 1, 0, 0, 1 that we wrote down a second ago. That's what reduced row echelon form is, and we'll see why that's actually very useful in obtaining a solution. Step 1, make this into a 1. Check, already done. We don't have to do anything additional to make this into a 1. So if that's already a 1, then you get to move on to this step where I want that 2 to be a 0, right? We're trying to make the matrix look like this. So how do I make a 0? The direction said multiply a row by a constant, and then you're going to add it to another row. So what I want to do is I'm going to multiply this top row by a constant, such that when I add it to this row, it becomes 0. So the operation that I'm going to use here is I'm going to multiply row 1 by -2. If this was a -2 above the +2, adding those together would make that 0. So -2 times row 1 plus row 2. I'm going to take that result and I'm going to place that into row 2. And that's the operation that I'm doing right here. So you can probably do some of this in your head, if not all of it. These are pretty straightforward numbers. Just for this first example to get started, I'm going to write down the work off to the side. So that top row times -2 is -2, -4, and -10. Keep the bottom row the same, 2, 1, -2. So we get, if I add vertically, 0, -3, and -12. Okay, so now that we have that result, that's what row 2 is going to look like. So create another matrix where row 1 is the same exact thing, but my new row 2, after that operation, is 0, -3, -12. Okay, so we've just made a 0 in the location we wanted. Next thing, we're going to rotate around counterclockwise, which would bring us to the -3. What do I want to be in that -3 spot? We want that to be a 1. To make a 1 at this stage in the game, you're going to multiply that entire row by a constant. Essentially what we're doing is we're just going to multiply that row by whatever the reciprocal is of that number that's in our 1 spot. So if I multiply by negative a third times the entire second row, I'm going to put all of those results back into row 2. The reason why we can do all these operations is it's really the same thing that we were doing with solving yesterday, right? Can I multiply both sides of an equation by a number like negative a third? Yesterday, we also solved systems by multiplying an equation by something and then adding it to the equation below it. That's what this is. And if you have the question, why aren't we just doing it that way again then? It's because we're going to build off of this. We're eventually going to extend this to what's called the 3x3 system, where there's 3 equations with 3 unknowns, and having some organization to it is really beneficial. So if I take that second row multiplied by negative a third, you get 0, 1, 4. I'm pretty sure we actually could have just done that without writing it off to the side, but just to show you what that would look like, here are the numbers that are going to come into my new row 2. So we've got 1, 2, 5. Bottom row is now 0, 1, 4. One more step to go. The last thing to get this into RREF, reduced row echelon form, make that into a 0. To make that into a 0, we're going to do something similar to what we did up here. I'm going to multiply a row by something and add it to another row. This time I'm going to take the second row, multiply it by negative 2, because if this was negative 2, adding it up to the 2 above it in row 1 would make that a 0. That entire operation I'm going to put back into row 1. So let's write down what that would look like. Negative 2 row 2 would be 0. Negative 2, and then at the end, negative 8. Row 1 is 1, 2, 5. Add vertically to get 1. This becomes our 0. Negative 8 plus 5 is negative 3. So if I recopy that matrix one more time, we get that this is the new row 1, 1, 0, negative 3. And then 0, 1, 4 is the bottom row. Okay, based on where we're at, we have actually now solved the system without maybe even realizing it. Because if I translate this back into an equation, right, based on how we started this whole process, this was 1x plus 2y equals 5. This last line right here now says 1x plus no y's equals negative 3. So from that result, we know that x equals negative 3. And down here, 0 x's plus 1 y equals 4. So therefore, y equals 4. As soon as you get your left side to be in this reduced row echelon form, the right side of the wall, your values of x and y. Okay. So definitely going to take a little while to get used to. We'll do another one for practice right now. All right. All right. Let's try something like, we have 2x plus y equals negative 5 and x minus 4y equals 2. First thing, create the augmented matrix. This is something that I'm hoping is one of the easier steps in the process. Create that 2x3 matrix with the coefficients from each equation. So we get 2, 1, negative 5, 1, negative 4, 2 for the bottom row. And the very first thing we start with is we look in the top left corner, and I need this to be a 1. Well, in the last example, it already was a 1, so that was good news. In this case, to make it a 1, you have 2 options. You can multiply that entire row by a half. That's how we made a 1 in another instance before, multiplied by the reciprocal of what's in the spot that you want to make the 1. I'm not going to do that, though. Can I just switch row 1 and row 2? That was actually the first rule that I wrote down earlier, is that switching row 1 and row 2. Because remember, it's essentially just saying, what if that first equation was on top? Would the solution to that system be any different? No. Switching row 1 and row 2 is the easiest way to get that to be a 1. Okay. Now from here, I want this number underneath it, the 2, to be a 0. So very similar to what we did up here. By the way, this number is not always a 2. I feel like it's been a 2 for the last couple of operations we've done. We're going to do negative 2 times R1 plus R2. And all that's going to be put into row 2. All right, I'm taking the training wheels off right away here. because I'm not going to write down all that algebra off to the side. If you liked writing that algebra, that work part that I was writing up here off to the side, this step and this step here, go for it. But I think you can handle this. Ready? Row 1's not going to change. 1, -4, and 2. The row that's changing is row 2. So -2 times 1 is -2, plus that 2 below it is 0. If that's not a 0, we definitely did something wrong. That was the whole goal. Make that a 0. Keep going with that, though. -2 times -4 is 8, plus the 1 below it is a 9. -2 times this 2 is -4, plus the -5 is a -9. So I successfully made that into a 0. Next thing I do is I go across from that, make this into a 1. And if you go out of order, you're going to find that your system really doesn't work out in the end. So the order that I'm going in is actually pretty important. All right, so I want to make that into a 1 by taking row 2. I'm going to multiply it by 1/9. Even though I'm saying row 2 times a 9th, you can definitely think of this in your head as dividing everything by 9. That's probably a little bit easier to get the result. So row 1's not changing at all. Row 2 is 0, 1, and then -1 at the end. And then finally, last step is to make that -4 above it into a 0. So that would be 4 times row 2 plus row 1. And that's going to be the new row 1. Okay, right? If this is a positive 4, adding it to -4 would make that a 0. So the last step in the matrix here, let's see if we can really extend this out here. Okay. In this last step, row 2 actually is not changing. 0, 1, -1. The row that I'm trying to change is row 1. So 4 times 0 is 0, plus the 1 above it is a 1. The nice thing about going in this order is that since this will be a 0, it's not going to change that 1 above it when I multiply by whatever this number is here. 4 times 1 is 4, plus the -4 is 0. Good, that's what I wanted to have happen. Last step, 4 times -1 is -4, plus 2 is -2. So we get the solution to the system, x equals -2, and then y equals -1. Okay. If you're feeling a little bit better about the process, that's good news. I'm going to do one more with you in this video, and then I'll let you know what the practice is out of the textbook for homework. Okay, last but not least, let's see if we can solve the system. 2x minus 3y equals -7. 5x plus 4y equals 17. Okay, very first thing we gotta do is make that augmented matrix. All right, once you make the augmented matrix, that spot where the 2 is has to be a 1. You can do a couple different things. We easily made that happen a minute ago by switching rows, but if I look right below it, I don't see a 1 there this time. So we're going to be forced into saying, all right, let's take row 1, multiply it by a half, and that will be the new row 1. Okay, so this becomes a 1, but then you're not going to like this one because already we get some fractions in the mix, right? So we've got -3/2 and -7/2. I like keeping it in fraction form. If you like decimals, I'm not too opposed to it, but you know, you can use a calculator for some of the operations if needed. Okay, next, where the 5 is, has to be a 0. How do we make zeros? We're going to take the top row, multiply by -5, and then add it to the row you're making the 0 in. Add it to row 2. That will become the new row 2. Okay, row 1's not changing. So recopy that. Row 2, I know this is a 0. All right, let's see if I can carefully do this. -5 times -3/2 is 15/2. Right, just multiply it by the top. 15/2 plus 4, which is 8/2, is 23/2. Okay. -5 times -7 is 35/2. To make a common denominator with 17, that's 34/2 for a total of 69/2. Okay, a lot of big math going on in your head there, but it's okay. Next step, we're going to multiply by everybody's favorite number to get that to be a 1. If I don't want that to be 23/2, I'm going to take row 2 and multiply by 2/23. That's going to be the new row 2. Row 1 doesn't change. Row 2 is now 0, 1. All right, 69 halves times 2/23. The 2's would cancel, top, bottom. So you're left with 69 divided by 23, which luckily that goes in really nicely. It goes in 3 times. This number's a 3. Last but not least, -3 halves has to become a 0. So that's going to require me to multiply the bottom row by 3 halves, positive 3 halves, and add it up to row 1. That will be your final row 1. Okay. So row 2, not changing this time. Row 1 definitely is going to be 1, 0 up here. Last step, 3 halves times 3 is 9 halves. 9 plus -7 is 2/2, better known as 1. So even though we have these scary fractions all the way in the mix, it's actually a pretty nice solution in the end of x equals 1 and y equals 3. It's going to feel a little bit uncomfortable at first, but I really want you to try to force yourself into this process, even though we know how to solve the system in a different way, because this will help you immensely, not only when we solve bigger systems, but when we do other stuff with inverses later on next week. Okay. So finally, before we take off from this video here, and I'll post this on the website too, guys, but in case you're watching, the homework that goes with this in the textbook is section 7.1, numbers 21 through 27. Okay, so not too many, but I think it's worth taking a look at that practice and getting some repeated practice with this new Gaussian elimination technique. Okay, any questions about anything, send them my way. Otherwise, we'll catch you guys later.